Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Today's episode, we've got a really interesting discussion with someone I've known for quite a while now and been really keen to get onto a podcast because she's a real expert in battery technology, I think. So it gives me great pleasure to welcome Isobel Sheldon to the podcast. Hi, Isobel.
Hi there, Ryan. How are you?
Great, thank you. Very good. And how are you doing?
Yeah, pretty good considering working from home, but busy as usual, as you know.
Yeah, it's interesting times at the moment. So, this obviously we're recording this via the wonders of the internet. So, apologies if it's not quite as good as a face-to-face, which we had planned or had been talking about. But hopefully, we can still have a good discussion. So, if you'd like to just start, Isobel, by giving us a bit of background in terms of how you got to be doing what you're doing now and how you got involved in batteries.
Well, I sort of fell into it back in the early 2000s. I was working for a company in Strasbourg. They were a supplier, tier one supplier into the automotive industry. And having spent some time in the defense electronics industry in the 80s and the 90s, I had some basic electrochemical knowledge. I wouldn't like to claim I'm a specialist, but I do understand the basics. And I just started to put together in my head, the fact Toyota had released the first generation Toyota Prius, and that was using nickel metal hydride battery technology. I'd come across lithium-ion technology, part of a hobby interest I had at the time, and was starting to understand how that operated. So I put two and two together in my head and realised that, even in those early days, electric vehicles were going to be part of our future. And I gave up my very well-paid job based in Strasbourg in France and set up my own company.
Oh, wow.
And initially I did consultancy, but then quickly realised that you had the cell manufacturers and you had the vehicle manufacturers, and you didn't have anybody in the space in between at that particular point in time developing the battery systems. So I raised some money from some high net worth individuals, put in the remainder of my life savings, and I set up a company called Amberjack Projects and went out and bought a Toyota Prius and worked with a company called NGCS in California in between as we developed some of the first plug-in hybrids powered by lithium-ion battery technology, and in fact became the first person in the world to commercially offer them into the marketplace. So that was back in 2003, 2004.
Oh, wow.
And then developed that technology, developed those designs, started peddling it around the automotive industry, and eventually ended up working for companies like Smith Electric Vehicles, Lotus, did an Infinity project, the Infinity Emerge Halo car, and then started working in the public vehicle sector, so buses mainly. And towards the end of the 2000s, we made a big push into working with bus manufacturers and developing some really large systems, sort of 150, 200 kilowatt hours, and ran some prototype and demonstration programs in Europe. The global financial crisis we survived it quite well in 2008 and 2009, only to be caught out by the European financial crisis. So as we moved away from passenger cars, which weren't quite ready to move into any kind of significant volume, it seemed that electric buses was a pretty good bet. And that was one of those markets that was going to move first. But of course, the European financial crisis meant that revenue dried up quite significantly. So unfortunately, we had to close the business. Following on from that, I joined Ricardo as a business manager specialising in batteries and was with them for a couple of years. And then I got headhunted to go and work at Johnson Matthey Battery Systems as their engineering and technology director, which I did for a number of years and helped the staff through the Cummins takeover of that particular division. And then after I'd done that for about 11 months, the opportunity to work at UKBIC came up. So I moved across to UKBIC in January 2019. So all in all, I've been about 17, 18 years in the battery industry. So probably one of the longest serving people in this industry, and certainly one of the first to build high voltage battery systems back in the early 2000s and actually put them into vehicles and put them on roads.
Yeah, and I mean, back then, sort of the world was a bit different. I remember, getting jokes about milk floats and such like all the time. So it wasn't the electric vehicle industry wasn't quite as in vogue as it is today.
Oh no, I mean, people were still just getting their heads around what was a hybrid, and we were coming out with the first plug-in hybrids.
Yeah.
And most of the people that knew me said, "You're going to do what?" They couldn't quite believe I was doing what I was doing. But it turns out, more luck than good judgment. Actually picked an industry that was going to have a future.
Oh, fantastic! So now you're at the UKBIC, and just for people who don't know what that is, could you just tell us more about what the BIC does?
Yeah, of course. It's part of the Faraday Battery Challenge, which is part of the Industrial Strategy Challenge Fund that was set up by the government a couple of years ago. So back in 2016, 2017, I was invited to join some technical working groups in looking at what the future of the automotive industry and spillover industries was going to look like as the use of fossil fuels declines in the future. And of course, the UK at that time producing about 1.7 million vehicles a year and producing about 2.5 million sort of higher end powertrains, 80% of which all that was exported. There was going to be quite a significant hit to the UK manufacturing sector as there was a decline in internal combustion engines moving forwards.
Yeah.
So out of those technical working groups, the Faraday Battery Challenge was born, and that's in three particular swim lanes. So you have the Faraday Institution, which is looking after applied research. So industry-led but academic executed applied research in battery technology.
Right.
And they were given £78 million. Then we come to the next swim lane, which is the CR&D programs run by Innovate UK. So they were given £88 million specifically to spend on battery CR&D. And then at the time, it was an £80 million investment in the scale-up facility. So one thing that's always been missing in the UK is that ability to take products and projects from the back end of the CR&D and demonstration phase and actually scale them up into commercialized manufacturing. So that's one thing that the UK has been particularly bad. So the UK Battery Industrialisation Centre is designed to provide that capability in the UK in support of the battery industry and hoping to grow that moving forward, as is the whole Faraday Battery Challenge. So it's quite a unique facility in the world. It's a nominal 1 gigawatt hour battery scale-up and manufacturing facility.
Oh, wow.
We're not a commercial organisation. We're not here to compete in the marketplace, but we're here to help companies that do want to become active in the marketplace to scale up their battery manufacturing capabilities. So that could be a materials development company. It could be a cell OEM that wants to put a battery cell manufacturing capacity in the UK. Or it could be companies that are looking at module and pack manufacturing as well. So we're really here as a support function to help that industry grow in the UK and benefit UK PLC.
Oh, right, cool. And the centre itself is, what kind of activities are planned? Because it's not built yet, is it? Or not quite finished yet at the time of...
Not quite finished. We moved into the offices about 4 weeks ago.
Right, okay.
So if we think about the timescale, the first spade in the ground was somewhere around the middle of March. So I think it was 11 months and 2 weeks to come from a greenfield site, where in fact it was a rugby field with rugby posts and a clubhouse, to a battery that's up and we could occupy the offices. I mean, that's as quick as the Chinese would put up a facility.
Yeah. And
so, notwithstanding the pandemic crisis at the moment, the timing plan is showing that we should be producing our own reference cells around about July. So we'll pretty much be sat in the first phase of the finished facility in July this year. And the scope of activities on site, we can come from the active materials that come into the business. So if somebody wants to come and build some cells whilst they're waiting for their own facility to be put up, they can come into UKBIC, and we can take the active materials, the anode and the cathode and the binders and the thickeners and the additives and the solvents, and we can mix slurries. We can coat electrodes, both anode and cathode, so we've got one of each. And then we can bring those together, slit and calender, and do cylindrical and pouch cell assembly as the first phase.
Oh, wow.
So as I said, cylindrical cells, 21700s, we can do from July onwards. We'll be making our first reference cells. And then 300 by 100 pouch cells towards the end of the year, from about November, December time.
So it really is a full battery cell production facility, and capable of some quite significant capacity as well. It's not a kind of lab. I guess it must sit somewhere in between being a research lab and a full kind of industrial manufacturing plant.
Well, yeah, I mean, it's not just cells. We will have module and pack capability as well.
Right.
So that will be up and running from about November time this year. Typically, we're going to come from TRL 7 up till about TRL 9, and MRL 5 up to about MRL 8 or 9. So it's a full scale manufacturing capability facility. As I said, it's not commercial, so we're not making commercial cells, but it's there to provide that gap. It's the ton scale. The labs that you talk about are generally working at the kilogram scale. Gigafactories work at kiloton scale, and we're going to be at the ton scale in between, that missing gap.
Wow, that's really it's fascinating. And is it looking like it's going to be sort of really busy as the centre opens? What's the demand looking like from the market?
So demand's looking pretty good, actually. With these kinds of facilities, you never quite know how they're going to be utilised moving forwards. But we're already starting to have to think about scheduling work coming into the facility and making sure that manufacturing slots are available for companies that want to come and use it. So we're seeing quite heavy demand on the module and pack side. And a couple of customers that are already committing to using the facility towards the end of the year.
Right.
But we're also seeing demand for things like electrode manufacturing. We're starting to talk about cell manufacturing with a couple of companies too. And luckily, we've built a very flexible facility. So if you need to come in and just make electrodes, we can do that. Or we can take it all the way through to a fully finished cells. Or even if you want to bring in your own electrodes and manufacture cells, we can accommodate that too. So giving that kind of flexibility to the facility so that you don't need to pay for the whole lot whilst you're using it. You only pay for the bit that you need to use is going to be the secret to our success moving forward.
I guess a key question maybe for some of the people who are listening, because it is we've got a good sort of international following for the podcast. Is it restricted to just UK companies that can use the facility, or will you work with global partners?
So we can work with global partners. There has to be some UK GDP benefit, some benefit to UK PLC. Yeah. So that could be supporting a technical centre in the UK, even if the manufacturing is done elsewhere, or even companies that are looking at becoming active in the UK economically but aren't yet. We see this as a tool to enable them to achieve that and reduce the risk. So a big part of what UKBIC is doing is reducing the risk for companies. We've built the facility at the ton scale so you don't have to. We'd rather you save your money and build the Gigafactory further down the road, or your battery pack manufacturing facility further down the road. Yeah. We're also here to provide skills training and upskilling.
I was just going to ask about that, because that's a big with any emerging industry. Corporates tend to want people who are experienced in doing what they do, but because people don't do a lot of battery cell production at the moment, relatively, certainly not in Europe, there's a big skill shortage of people who know what to do in that space, isn't there? So
there's a huge gap, and you can't go on many courses that teaches you how to do it. No. So a big part of what UKBIC intends to do is, as you come into the facility and you start making your product using our equipment, we're expecting you to bring your staff in as well. and they can get on the job hands-on training in how to operate these processes and familiarize them with equipment. Or even if you're thinking about buying equipment and you're not quite sure what you need to buy, coming into UKBIC and utilizing what we've got will help you make more efficient capital decisions moving forwards.
Wow. And I know one of the big things that there was a lot of speculation about and people were talking about was the possibility of another Gigafactory coming to the UK, because obviously we've got the one up in Sunderland attached to the former Nissan battery manufacturing. But do you think it's realistic in terms of another Gigafactory coming into the UK? Do you see the potential there for a UK version of a Northvolt or something like that?
So I think there's definitely the demand profile for it. If you look at the modelling as to what the demand for battery systems just for the UK domestic market is concerned, you're talking about over 100 gigawatt hours. And to give you an idea, the Nissan facility is about 2 gigawatt hours. So, it's a 50-fold increase in requirement by about 2030 to 2035. So if you think about a gigafactory, can be anything from 15 gigawatt hours to 30 gigawatt hours. We could be talking anywhere between 3 and 5 gigafactories required just in the UK.
Wow.
If you gaze across the English Channel,
yeah,
and look at the demand over in Europe, which is 10 times bigger, there's a significant export opportunity for the UK as well. So if you build a factory, is it going to be utilised? I think with the undercapacity in the world for cells and battery packs at the moment, I think it's a pretty sure bet that you've got a good investment on your hands if you do that.
Oh, if only that'd be the things that dreams are made of. I'd love to create a UK Northvolt. Maybe we'll do that next week, as well.
Yes, let's just go and raise some money. I think it requires a few billion to do it, but
one or two. I've heard 1 or 2. Yeah, I'll have a look down the back of the sofa. So I've got, and we get questions all the time on battery technology. I would say that the incoming questions into the podcast, there's a huge number to do with battery tech, current state of the art, what's coming in the future. So I would like to bounce a few of those off you, if that's okay.
Yes, of course.
And maybe just if we can kind of talk about some of the things that are happening now in terms of the state of the art and what's coming down the line. So one thing recently that we've had a lot of interest in is silicon anodes. So that's something I know absolutely nothing about. But people are asking us basically either what are silicon anodes or what is the sort of hold up that's stopping silicon anodes getting into more widespread production. So what do you know about silicon anodes?
So interesting question, and I will caveat this by saying I'm not an electrochemist, but I do obviously have experience of what this is.
Yeah.
So silicon anodes at the moment using a mixture of natural and synthetic graphite in most of the lithium-ion batteries out there in the marketplace at the moment. And we've heard a lot about the cathode material capacity needing to go up, which is a perfectly valid route of improvement. When you come to the anode, there's not an awful lot you can do with graphite. You can tinker with it, you can put some additives into it, but fundamentally its capacity is fairly limited. So silicon offers an opportunity to significantly increase that capacity. I wouldn't like to give you a doubling or a trebling capacity for the anode, because it's not my area of speciality, but it's a significant uplift in capacity. And you're already seeing silicon materials coming in small percentages into lithium-ion batteries that are currently in commercial manufacturing.
Right.
The big problem with silicon is that all materials expand and contract as you collate and intercalate lithium-ion backwards and forwards, the ions backwards and forwards.
Yeah.
The problem with silicon is it increases 300%, whereas in a normal material it's sort of 5 or 6%. So you end up with a lot of mechanical degradation. The material tends to crack and split and fall to pieces. So the cycle life consequently is very, very limited. Now, there are a number of organizations around the world that are looking at different systems and different methods to be able to combat that and be able to accommodate the swelling without there being this big mechanical degradation within the material. and some of them are making quite significant progress. This makes it quite interesting because it gives an opportunity to have a process which could, not definitively, but potentially could be dropped into the existing lithium-ion manufacturing process, which makes it really, really attractive. But the problem is you need to overcome this problem of the 300% expansion. So are we going to make progress in this area? From the results I've seen from various companies, they're making some good progress. Are we there yet to have a very high loaded silicon anode material? I don't think we're quite there as far as checking it as being fit for purpose as far as cycle life and safety is concerned. I think there's some way to go, but it is showing promise, and I think that maybe at some point in the future it might be something we'll see in a commercial cell.
Oh, great. Is it something that is being worked on actively in the UK? Do you know?
Yes. Not only is there research going on, but there's a company called Nexion who's very active in this particular field and have some interesting ideas that could potentially be commercialized. So they're working very hard in trying to bring their material to visibility and obviously to scale production.
Right. Okay. Fascinating. So hopefully that tidies it up then in terms of why people are looking at silicon anodes. The next thing that we are asked about all the time is solid state technology. So this is, I think there's sort of varying different levels of solid state from what I can establish. But what's your take on what's happening at the moment with solid state battery technology?
Well, there's quite a few different approaches to solid state, especially on the materials front. People using different materials or companies investigating different materials. The problems that you have with solid state are pretty well known. You get voiding, you get dendrite formation, because if you're using a lithium metal anode, you're stripping material away and then trying to electroplate it back. That's how it's working through a separator material, and that separator material is a solid electrolyte. So the surface chemistry in trying to get that to work is particularly challenging. And I hear a couple of people in the industry quip that the stuff that we can make doesn't work and the stuff that works we can't make, which is probably oversimplifying it to a certain degree.
Yeah.
But there's a significant amount of work that needs to go into making this happen.
Yeah.
So obviously capacity is one. If you can use lithium metal anode safely, then obviously you get very high capacity. Reduction in flammability is one of the main drivers. So you're not using a flammable electrolyte, using a solid electrolyte that was much more difficult to set on fire. So the improvements in capacity and safety could be dramatic. And progress is being made. I'm seeing some feedback on developments that are showing pretty good cycle life,
right.
But still have some fundamental problems that need to be overcome. The big problem with solid state is that it's the scale up in the manufacturing. It's not going to be a standard reel-to-reel coater winding type assembly process. So whilst the world is scaling up for mass lithium-ion manufacturing for electric vehicles and the hundreds of billions of pounds that's going to be spent globally to be able to achieve that, come along with a new technology that suddenly means you have to junk half that equipment and start again. It's got to be a pretty compelling economic case to get people to do that. So I think fundamentally we're stuck with lithium ion for the next 7 to 10 years because of the investment that needs to go into ramping up the scale.
Yeah.
And that really gives the people working on solid state a bit of time to get this right. So by the time they are ready to commercialize, hopefully the electric vehicle market and all the adjacent markets like off-highway and aerospace are going to be willing to look at doing something a bit different moving forwards and potentially make different investments.
And do you think, because there are a couple of companies that are talking about having solid state in the market quite soon, like within the next year or so, and basically my take on that, or what people have told me, is that it's not really proper solid state technology. It's kind of somewhere in between a full-on solid state battery and a conventional lithium. So is that would that kind of follow with your understanding and thinking of it as well?
Yeah, I mean, there's work that's been going on semisolids and geltype materials. in theory, solid state's been around for quite a while. Belcore with valence technology way back in the early 2000s. They were using like a gel material in a matrix captured in a matrix in the polymer material. So there's always going to be variations on the theme that could potentially come and provide some advantages.
Yeah.
I don't think they're going to provide the big step changes in capacity and safety that solid state offers. So
right.
I think adoption of those closer to market technologies is probably going to be limited because of the scale that needs to go into stepping up to the EV challenge that we've all got in front of us.
Yeah, and well, that's an interesting question, and you actually mentioned it just now in passing, but you talked about the reel-to-reel part of the process, and it seems like in terms of the really, really high volume manufacturing processes that are needed to make the billions of cells that are going to be needed for electric vehicles and like you said, all the adjacent markets, it doesn't seem to me like there's a decent alternative for that really high volume production to reel-to-reel. Are you seeing a potential for sort of any alternate production methods, or do you think reel-to-reel is here to stay?
I think we're going to be stuck with reel-to-reel for a while. I think there are many improvements that can be made to the manufacturing process. I think fundamentally using reel-to-reel is going to be the mainstay. But adding in, new deposition technologies, there's quite an opportunity to improve the engineering of the electrode. So quite clearly, the electrode is the basic part of the cell as an assembled component or a coated component. If you can improve its performance through engineering it in a more interesting or clever way, that's going to have a knock-on effect and improve cell performance. I think that, this technology has been around since the 70s. It was originally invented to create magnetic tape. Remember the compact cassette?
Yeah.
And videotapes. When Sony were looking at commercializing the first lithium-ion cells, they were like, "Oh, how on earth are we going to do that? Oh, we've got a bit of equipment in the corner that used to make tapes, so we'll go with that."
Yeah.
So fundamentally, we're using 1970s technology, although vastly improved and much more efficient. But at the moment, it remains probably the most efficient way of manufacturing the electrodes. And interestingly, you're starting to see coater dryer sizes go up. So the coaters we've got in UKBIC are 40-meter coater dryers. And if you go around any manufacturing facility in the world, you will see exactly the same equipment being used. However, companies are starting to look at 60-meter coater dryers. So quite clearly, the larger the machine, the higher the throughput that you've got.
So just explain that. First of all, what's a coater dryer? And secondly, what does the 40-meter or the 60-meter, is that the length of the machine or the length of the product it can handle or the width? Yeah, what's a coater dryer? Start with that one, and then we'll get to the next question.
So a coater is a reel-to-reel machine where you unwind a foil, you coat the anode or the cathode, and you coil it back up at the other end.
Right.
And in between those points, after you've got your slot die, your comma die coating head, there are solvents that are used in the anode and the cathode. So in the cathode at the moment, it's NMP, which is not the most friendly solvent you can imagine and requires careful handling. The anode tends to use deionized water. So lithium-ion cells need to be dry. Water tends to cause big problems as far as the electrolyte is concerned, and obviously you've got lithium in there.
Yeah.
So you need to have all the solvent and all the water taken out of the coated material before it gets rewound and then slit and used to assemble cells.
Right.
So in between the coating head and the rewinder, you need to have dryers. So these are big drying ovens, which the coated material on the copper and aluminium foils passes through, and it evaporates the solvent or the deionized water. The DI water is fairly easy to manage, but the NMP, the solvent, needs to be recovered because it's got some health and safety considerations around it.
Yeah.
So these machines tend to be in industrial facilities about 40 meters long.
Right.
So if you're passing the anode or the cathode material through a dryer, and it's only 40 meters long.
Yeah.
It's only so fast you can run it because you're temperature limited. You can't go too high in temperature.
Yeah.
And increasing the length of that drying phase to 60 meters means that you can actually run the machine faster and still get the material dry at the end of the process.
Okay, so the 60 meters is literally the length of the machine. So that's a colossal machine.
It is. I mean, the coater bit's actually not too big.
Yeah.
Probably talking about sort of 7 to 10 meters long, maybe a bit longer, and the rest of it is all the drying zones.
And on that, one of the technologies that's potentially been talked about recently, I think Tesla experimenting with dry coating. Have you seen much of that?
So I've seen the reports and obviously seen the companies they've bought to acquire that technology. And dry coating does represent a lowering in cost, a significant lowering in cost, because quite clearly, if you don't need to run a dryer, you can produce it an awful lot quicker. So an interesting development. I'd like to see evidence of that being used in production. I'm sure it's not at the moment, but I'm sure it's all knowing how Elon Musk works and how bright and smart that guy is, he will find a way to commercialize it.
Yeah.
So I think what the benefit is going to be and how much that's going to impact in cost. You can see the predictions, but the reality of that would be interesting to find out.
Yeah, it's super interesting because there's two elements, isn't there, really, to the cost of batteries for EVs or for anything. One, you got the raw material element of the cost, which is obviously significant, but then the kind of processing cost and that turning it from raw chemicals into a finished battery cell, and there's quite a lot of processing steps along that way, isn't there? So the opportunities on the material side are getting better use of the active materials in the battery, and then on the processing side, being able to take out or optimize or reduce the processing time or the energy input cost into the manufacturing, because there's also quite a lot of energy required. So it's interesting to see people kind of working across all of it, really, to looking for incremental improvements and also these big potential step changes. But the reel-to-reel process is, it's fascinating. For some reason, it reminds me of being in like a newspaper plant, just seeing all these sort of huge amounts of sheet material flying all over the place and being handled. It's quite an amazing thing to see working and in operation.
Well, incidentally, actually, when you start talking about the staff that you require to manufacture all the way through that manufacturing chain, there are allied industries where there are relevant skills. So printing in newspaper presses actually does have a very similar skill set to coating electrodes. So you can find coating experts in a number of different industries that could be brought into battery manufacturing. Actually, you raise a very interesting point about the cost stack up. If you look at where the material's dug out of the ground and then where it's delivered as a finished material, there's a tremendous number of processes that sit in between those 2 points.
Yeah.
And cutting down the carbon footprint of the supply chain is going to be a really important part of what we do moving forward.
Yeah.
So currently you have materials that end up going around the world a couple of times before they actually get assembled into a product that can be utilized, and trying to cut down on that is a really important part of what we're trying to do moving forwards.
Yeah.
And interestingly, the UK is actually in a fairly good position. So although on the nickel, we don't actually mine the nickel, we do have the second largest nickel refinery in the whole of Europe, based in South Wales and Clydach.
Oh, really?
And they already produce refined nickel that can be used in battery technology. There are a couple of intermediate processes that it needs to go through before it can be used, but the basic material, the refined material, is produced in the UK. On a similar scale, on the anode, about 20 or 30% of the anode of a lot of batteries that are used in the world is made from synthetic graphite. The synthetic graphite comes from needle coke, and the best quality needle coke in the world comes from North Sea oil. And about 30% of that market is supplied by a company called Phillips 66 based in Lincolnshire. So two of the significant elements in the battery supply chain are already here in the UK.
Oh, wow.
So if we can get the intermediate processing done here in the UK, then we can start to reduce the carbon footprint of those materials. And because we've got a very green grid and it's getting greener, we have a good opportunity to deliver on that promise. Of course, you mentioned that it's very energy intensive, and energy here is much more expensive than it is in China.
Yeah.
So we've probably got to be a bit more clever with the processing to reduce the energy and the value add, or work a way of, actually reducing the energy costs so that it becomes economically attractive to do it here in the UK. But we've got a good starting point.
That's complex, isn't it? Because the energy cost in China arguably is not really a true cost, because it's quite a heavily state-controlled market. So I don't see it going that way in the UK anytime soon. But the opportunities for renewables to sort of drive your battery process are great. I had a fascinating discussion the other day with a guy called Gerard Barron, he runs a company that are doing they're basically recovering battery metals from the ocean floor. So it's kind of, I'm loath to call it underwater mining, because they're not really mining. They've got a source of the materials that are required for batteries that are just sort of sitting around in what he described as like small potatoes in the deep ocean floor. Apparently, they're accessible and incredibly pure. So the carbon cost of getting from these nodules into materials that can be used in battery production was, I can't remember exactly what he said, the number, but it was huge. It was like 70% less than conventionally mined materials. And it had a huge impact on the CO2 of the finished battery. So it's really, might not turn into anything, but he was really clever guy, very passionate about what he was doing, and it was interesting just hearing of a completely different source for those really important raw materials.
Yeah, I think it's interesting because, if I teleport myself back to the early 2000s when I stood there with my hands on the hips going, this is going to be big in the future, but nobody would listen. And then sort of fast forwarding to today where everybody's listening to it and everybody's piling into it.
Yeah.
And the more brains that think about this and the more people that start investigating, the more possibilities there are moving forwards, and some great innovations to come to not only the battery tech itself, but also how do we fill up this supply chain? How do we localize it in the UK to make sure we can feed the factories?
It's amazing.
So, yeah, I mean, I think it's great.
Like 10, 15 years, it's gone from the challenge being the crazy people like me and you going, this is going to be a big thing, and everyone else going, no, it'll never take off, to now the challenge is everyone going, well, there's going to be so much demand that it'll be impossible to meet the demand with what we've got from materials, and how many mines are we going to need to have to satisfy all this? It's sort of the challenges. I guess people will always find problems, but the challenges have flipped on their heads in quite a short space of time.
Yeah, and also the misconceptions over materials as well. There's lots of nickel, there's lots of carbon in the world. Quite clearly, we've got too much carbon. Lithium isn't quite the problem that everybody keeps reporting it to be. There's plenty of it. It's just thinking of different ways to get access to it. And obviously, owning the right to the resources is going to be a significant part moving forwards. The big problem is cobalt, and trying to reduce that cobalt content. Really, if you go and listen to the experts in that field, that there is an impact to reducing cobalt, because even if it's not done in the right conditions, there are people whose livelihoods depend on mining that material.
Yeah.
And those people will struggle even more when we stop buying it. So we've got to think about support for those communities and those countries that are going to lose revenue in the future, and their populations are going to suffer as a result. Not saying that the mining conditions are acceptable by any stretch of the imagination, but there is that to consider. And cobalt is one of those materials that, we're going to struggle to get rid of it completely. We may get down to acceptable levels in batteries, but it's there for stability. It's something, if we take it out completely, we end up with stability problems within the cells.
Right.
So it's a conundrum that needs to be thought about and fixed. But there's also the human impact, further upstream in the supply chain, that needs to be carefully thought out in conjunction with that.
And what is so when, because that neatly segued in, my next question was about reduction in cobalt content. What is it that that people are doing to get such significant reductions in cobalt? Because we've gone from kind of 10% to 2% or less in quite a short space of time. So what's kind of enabled that transition?
Well, we went from 30% to 20% to 10%. And the next generation will probably be half of that, will be about 5%.
Yeah.
So it's looking at clever additive systems to go into cells to try and improve the stability that don't use cobalt. It's all about that stability and making sure that material is safe and can cycle well. So it's really a question for the electrochemist, not a question for me. But I know a tremendous amount of effort is going on in that particular field. And I think that, the holy grail of having a cobalt-free battery is what everybody's working towards. But I think there's a realization that that's going to be quite difficult to deliver on.
Yeah.
So as the global demand for batteries increases, there is a benefit, because the percentage increase in cobalt, hopefully in the future, will be less steep.
Yeah.
So the whole thing will rely less on cobalt than it has done in years gone by.
Yeah, it's really interesting to see. I guess, I mean, one of the challenges, I think, and you're right in the middle of this, so you must see this, is that there's so much work going on in so many different areas. There's a lot of moving parts at the moment to the battery scene, and just kind of keeping a handle on everything that's going on and making sure that you're not working on something that's going to be obsoleted by someone else's innovation must be quite difficult at the moment. Do you see that as being a problem in the space?
Yeah, I mean, whilst the opportunity to have game-changing improvements in energy density a little way off yet, it's probably less of an impact as far as I can see. The day the person turns up and says, I've just overnight doubled energy density, is when people are going to start looking at the investments they've made and start to be concerned about that. But I don't see that happening in the next 5 to 6 years, to be honest. I think solid state is towards the back end of this decade as a proper commercial widespread product.
Right.
But you're right. I mean, there's a tremendous amount of work going on left, right, and centre all around the world, and keeping tabs on all of it is nigh on impossible. I'm fairly well placed to have visibility of a lot of the major developments, but occasionally, people come and go, have you seen this? And I go, wow, no, I haven't seen that. So I don't think anybody can keep abreast of everything that's going on.
Yeah.
All we can do as a global community, because this is a global push, we need to keep collaborating and keep cooperating to make sure that we can all achieve this goal of reducing our dependence on fossil fuels and improving local air quality. I think it's such an important thing for the world to do.
Yeah. I agree 100 million %. So the elephant in the room then is often with lithium batteries, people get onto the safety angle, so some of the sort of things that you see in terms of the potential for fire risk and that sort of area. What do you what's your take in terms of what's happened with battery safety and what are the kind of main opportunities in terms of improving that further?
So there are a number of companies around the world that have got very, very good safety records as far as themselves are concerned. I think AESC would be an example of that. Their number of incidents, global incidents, is actually incredibly low, lower than you would normally expect.
Yeah.
There are other manufacturers around the world that have scaled up really very quickly and have a much poorer safety record. So I think there's a lesson that can be taken from that. Yes, we're in a race. We've got to do things really quickly. But that's absolutely no reason to push caution to one side when you're developing and designing these systems.
Yeah.
I think that companies and individuals that have a good track record of doing this kind of development really safely and having product out there in the marketplace that's provided good service, I think those people are going to be in demand, because that's what we've got to focus on moving forwards. So cell safety is one thing that I think is really, really important, and the drive to reduce cost cannot be at the compromise of safety.
Yeah.
The next level up is the system level. So yes, lithium-ion cells, there is a risk. I think we all understand that. But engineering that out at a pack level and putting the mitigations into the pack to make sure that if there was a catastrophic event with the cell, it's contained and it doesn't spread and it doesn't propagate throughout the entire pack. So I think we've made some significant progress over the last 4 or 5 years in that particular area. Is there more progress we can make? Absolutely. I think aerospace is one area where some of those innovations are going to come from. If you have a problem with your electric vehicle and you're driving down the road, you can pull over at the side of the road and get out. You can't do that at 30,000 feet.
No, not easily. Not without messing your hair up, anyway.
No, absolutely.
Yeah. Okay. And so I guess from that, a lot of the safety angle comes from basically good manufacturing process control, as much as it does from the kind of chemistry and actual materials technology in the product.
I think it's chemistry, it's good design practices. I've suffered from making those mistakes in the early 2000s myself, so I learned the hard way before you could go online and Google it. So design is a really, really critical part of that, but also consistency in manufacturing. So you want to make your product consistently at the same quality, but you also want to make sure that you can do it at the right yield with the reduced scrappage to make it economically viable. So really in the battery industry, it's a multi-pronged thing, and you need to have people that have got specialist knowledge in each of those areas to be able to make this a viable, economic and useful product going out into the marketplace.
Yeah. Okay. So last question then. Do you see there being any viable alternatives to lithium on the horizon coming for the automotive market?
$64,000 question. I wish I could answer that.
Okay.
So I think on the horizon, not at the moment. There are alternative chemistries. So sodium ion shows some promise in certain markets. It has the opportunity or the perceived opportunity to lower cost. But that does sacrifice energy density. There are high power versions of that technology that could be quite interesting in things like mild hybrids or grid scale energy storage, those kinds of markets. But I think for the majority of the bell curve in the automotive industry, lithium ion is going to be where it's at for the next 5 to 7 years.
Right.
And if you think about the further, the future technologies that could come along to replace that, they're still using lithium. Lithium metal anode. It's the lightest metal in the book. It's got a lot of advantages. Even if you went to Star Trek technology, they were talking about dilithium crystals. So even a couple of 100 years from now, that may be what we're still using. But I'd love for somebody to come up with a material that's different, can be made more cheaply, can be made more safely and more sustainably. But I think we've got to wait for those developments, and I don't think they're going to be coming in the next 5 to 7 years at least.
And actually, I said that was the last question, but I've got one more for you. Sorry. So thinking about the lithium chemistry, then most kind of OEMs have gone down the NMC route. Other than in in China, there seems to be a lot of people, or almost like a resurgence of LFP type technology. What do you see? You know, do you think there's a reason for that? Is the sort of use case particularly different, or has that technology improved significantly?
So the technology has improved. LFP technology has made progress. The energy density has improved. Is it anywhere near NMC? No, of course it's not. You're probably talking about in between sort of 60 and 70% of the capacity of NMC.
Right.
I think it's really interesting because I spent most of my early lithium-ion career before NMC and NCA came along. Cobalt oxide was the only alternative.
Yeah.
Promoting LFP as a safe alternative, long cycle life,
Yeah.
good safety, lower cost.
Good old thunder skies, yeah.
Yeah, so it's material I know pretty well. I think the resurgence is really interesting because there's been a big focus on, trying to get to that 400-mile EV range.
Yeah.
Majority of people drive 30 or 40 miles a day. I think, again, Elon Musk has been extremely smart because he's realized that the number of cars that actually use their full range every day are actually quite small.
Yeah.
So to reduce the cost of entry, for car buyers to go and buy an EV, to go LFP and provide a slightly more limited range but much lower cost vehicle at the same quality levels, for the rest of the vehicle, I think it's a really smart move. And I think a number of manufacturers could probably take a leaf out of that book and go, actually, LFP is offering some advantages here.
And of course, because it's not a conversion. The car that's going into is a ground up EV design. They've got the space. They've got plenty of space to sling a relatively large battery underneath, rather than trying to kind of shoehorn it in. With the best of intentions, an awful lot of the other EVs are kind of sharing platforms with internal combustion engines that weren't necessarily natively designed to be an EV. So it's difficult.
Yeah, I think the Flex platform's got a limited life. And when people start driving EVs, I've been driving EVs for 17 years. From prototypes through to production vehicles, and even being handed prototypes when I've got to companies in China who said, "Oh, Isobel, can you review our car for us, please?" And sort of handed me the clipboard to do the drive analysis.
Yeah.
But I think that if you can get to a point that Tesla's got to where the dynamics of the vehicle and the efficiency of the vehicle has been so well engineered, you can start looking at maybe some of the cheaper, lower performing alternatives and still have a really, really good vehicle for the road. You look at some of the work that they've done on heating, ventilation, air conditioning, and drive system, power electronics, e-machines, and how they've started to integrate these into single units to reduce the production costs as well as improve the efficiency. Suddenly having the latest thing in energy density becomes not number two, but probably less critical for certain types of vehicle applications.
Yeah, especially congested Asian roads in particular.
Or London, give me a Range Rover powered by an LFP battery. I'm probably happy for every single day.
Yeah, that's true. That's very true. Congested cities, full stop. That was, okay. Fascinating. Well, Isobel, the time has absolutely flown by. We're over the 45 minutes, but I think that's definitely been worth it. So thank you. Thank you very, very much for taking the time out to talk to us today.
You're very welcome, Ryan. It's been my pleasure. Thank you for inviting me on the show.
That's all we've got time for today. I found that really useful, so I hope other people got some value out of that as well. If you've got any questions that you would like answering, so there's about a 3-month backlog of questions just been answered there in that one podcast episode. But if you've got any questions that you'd like answering, do get in touch and let us know. I'll put some links in the show notes so you can find out more about the UKBIC and more about Isobel. And don't forget to subscribe to our channel, to give us a review or hit like. We'll be putting more podcasts out over the coming weeks and months. So we've got some really good episodes coming up. And Well, hope you get lots of value out of those too. So, like I said, that's all we've got time for today. I really look forward to speaking to you again soon.